Hey there. As you might know, Postgres has a neat feature called logical replication. With logical replication, you can create a replication slot on your Postgres database, and then you can subscribe to that replication slot to read every single insert, update, or delete that happens in your database. The logical replication slot is what's behind change data capture tools like Sequin that allow you to take the changes as they're happening in Postgres and stream them to downstream systems like Kafka, SQS. You can replicate data to other data stores. And you can do this in order to power audit logs, to trigger event workflows for event-driven systems, to replicate data from one system to another, to keep caches or search indexes warm. So the replication slot is really the entry point to turn the data at rest in Postgres into data in motion, or to unlock the data in your Postgres database in a really powerful way. So without a replication slot, you'd have to resort to polling Postgres to detect changes, which can be very inefficient or slow and doesn't allow you to get the rich messages that the replication protocol does. So for example, the replication protocol gives you deletes, which of course you can't get by selecting from tables. And it also shows you every individual message as well as what changed in that commit. So you can see the old record and the new record for an update, for example. So it's a very powerful construct and protocol. And GenStage is what Sequin uses to power its data pipeline to stream out of a Postgres replication slot. And GenStage is a very cool library for Elixir for building your own data pipelines. And so I'm going to talk briefly here at the beginning about what the replication protocol is, how it works, and then we'll talk about GenStage. And then in this video, I'm going to show you the early commits for Sequin's SlotProducer. We just did a refactor of it recently, so it's fresh on my mind. And you'll see layer by layer how we build up a producer that is able to connect to a Postgres replication slot, stream in TCP messages, parse them, and then send them to downstream consumers. And so with that knowledge, you can build your own data pipelines. You can tap into the replication protocol yourself, or you can probably come up with a lot of ways to use what Sequin's already built in your own applications or workflows. Let's start with some of the background knowledge that you should have around how Postgres works to really get the most out of this video. Just a couple of things I want to make sure that you know. So first, every insert, update, and delete, as you might know, is committed to the Postgres write-ahead log, or WAL. Its primary purpose is for crash recovery, but you can think about it as an append-only log of the inserts, updates, and deletes that have happened in the database. When you create a replication slot is a way for downstream subscribers like Sequin to receive this ordered list of changes that have happened in the database, and to do so with at least once delivery guarantees. And so the replication protocol very much builds off of this write-ahead log. And the only other acronym that's worth knowing around this protocol is the LSN, or log sequence number. This comes up a lot in Sequin. The log sequence number is the byte offset of a given transaction. And so if I insert a row and it's all by it, that insert's happening all by itself, it might happen at some log sequence number of 1, 2, 3, 4, 5. And then a subsequent transaction that occurs will have a log sequence number that is some number greater than that. And if I have my next transaction contains both an insert and an update, both of those will receive the same log sequence number because they're wrapped inside of this transaction that has a log sequence number of, let's say, 12444. So these are made up numbers, and again, these are byte offsets. They increase by quite a bit between transactions and depend on how big the transaction was and how much space it took up in the write-ahead log. So that's really just the background knowledge for the Postgres replication protocol. GenStage is a library in Elixir for building data processing pipelines. And so you can have different stages where, for example, stage A is producing data or messages, stage B is doing some step, it's both consuming and then producing messages to stage C, which is the final stage in the pipeline. So Sequin is built on top of GenStage and uses these different stages to both pull in messages from the Postgres replication slot, do some processing with them, and then send them to downstream sinks like Kafka or SQS. And so it gives us a number of nice, we could build something like this ourselves using Elixir's Gen server, but it gives you some really nice constructs like subscription. So it helps you wire together these different Gen servers and their life cycle. And it gives you a really nice interface for passing messages along the stream. So if I go to here, you'll see that, you might recall that with Gen server, you can return a reply tuple, reply okay, and then state. With GenStage, it adds another element to the reply tuple or to these sort of return tuples that is the messages that you might want to pass downstream. So it makes it very easy for you to just emit messages, and then it figures out how to route them to consumers and which consumer to route them to. Finally, it has this concept of demand, which I'll talk about now. So when designing a data pipeline, back pressure is a really important attribute that you need to take into account. How do you handle it? And ideally, back pressure comes from the end of the pipeline and then ripples up through the pipeline. So if you're in a situation where these consumers are hungry and they're idle and they have nothing to do, then they should each basically tell the producer, hey, I'm ready for more work. And that's captured in GenStage by this concept of demand. And then if a consumer is completely pegged and it can't handle any more messages, then it won't send any demand to the producer, and the producer can then know that the downstream is totally blocked, and then it can perhaps ripple that state of the world upstream. So this allows you to handle. So GenStage gives you this concept of demand, which it automatically manages for you in order to help you around with back pressure. So we'll see how demand comes into play in Sequin, but the high level overview is we're going to be working on SlotProducer today. And SlotProducer is the entity, it's a GenStage producer that connects to a Postgres replication slot. So when the pipeline first starts up, all of these consumers will send some amount of demand to the SlotProducer. Demand is like literally a number, which is how many messages I can handle. And so a good default, for example, is 1,000. So all the consumers might say, hey, I'm ready for 1,000 messages. And so the SlotProducer, this is what GenStage handles. Underneath the hood, GenStage keeps track of how many messages each consumer is demanding. So in our empty state, all three of them right now are all demanding 1,000 messages. Then SlotProducer connects to Postgres. Postgres begins receiving messages, and we'll see all the inner workings of SlotProducer and how it handles these messages. And then it will produce those messages to the downstream consumers. And so, for example, it might route this insert message to this consumer, and then GenStage will keep track of the fact that we've satisfied 1 unit of demand in this consumer, right? Now, imagine that we are getting totally bogged down and there's tons of messages coming in, and for some reason, these consumers are unable to keep up with all the messages that are flowing in. And these all drop to 0, right? Which is to say, we've satisfied all the demand they've sent to us, or the SlotProducer has satisfied all the demand they've sent upstream, and they haven't demanded any more messages because they're just busy. They're over here completely pegged at 100%. So in that case, we now have control to introduce back pressure in our system. And in a CDC pipeline, that back pressure comes in the form of basically not reading more TCP messages in from Postgres, sort of putting a pause right here in the pipeline. And so by designing our data pipelines, having the end of the pipeline ripple up demand, we can handle back pressure in a really nice way. Now, obviously, if this is totally pegged and we're not reading from replication slot, we now have other issues. You're always going to have issues when you have any sort of blockage in a data pipeline. But this allows us to have sort of one central location where we know sort of the state of things and how things are going downstream. Now, of course, once this consumer clears up and it empties, it's able to get out from underneath its backlog here, it can then send a renewed demand up to SlotProducer. The pipeline's healthy again, the blockage is cleared, and we can keep sending messages. So this idea of demand and starting from the right-hand side of the pipeline or the end of the pipeline and then propagating up gives us a really smooth way to build our data pipelines and to handle back pressure. So let's hop into it and let's build up this SlotProducer. We recently did a refactor of it, so I'm going to walk through the different commits and layers as we built up the SlotProducer relatively from scratch all the way up to something that works in production for handling replication messages from Postgres and fan them downstream. SlotProducer is a GenStage producer. It connects to Postgres and receives replication protocol messages, and it will send those messages downstream to consumers. So this is the very beginning of SlotProducer here with just the basics of connecting and receiving protocol messages. We like to represent state in our gen servers at Sequin as structs. So this is the state struct for SlotProducer. And we'll see what each of these properties do in a moment, but as a quick overview, the protocol on state is where we'll store the Postgres protocol struct. So when working with a Postgres connection, Postgres uses a protocol struct just to maintain state about the connection. So we'll pass this in all of our queries that we make back and forth to Postgres. ConnectOps is a keyword list with things like hostname, port, database for connecting to Postgres. Start replication query. We'll see what this query looks like in a moment, but this is the command that we run after we've connected to Postgres to start the replication protocol. There's a callback. We want SlotProducer to be relatively isolated from the rest of our system and our internal data model and internal gen servers. So we use functions as callbacks to control what happens during connect failures or what have you. So that's one example of that here. We'll see how these come into play soon. When we can't connect to Postgres, we want to continue to try to reconnect to Postgres. And for timers, we like to have them be overridable on gen server boot. That makes it a lot easier to test. So in tests, we can set this interval super low for tests that care about reconnecting. And then for other tests or for production, this can be at some sort of default higher value. And then we have the status of the connection with Postgres. Last commit LSN is tracking where we are in the replication slot in terms of what we've processed, what transaction we just processed. We'll be doing a lot more around state tracking later on. Demand is GenStage demand, which we need to manage ourselves here. And then we have this field accumulated message binaries. And so this is where, as we're receiving protocol messages from Postgres, we'll be putting it into this data structure. Note that it's a map and it has fields like count, bytes, and then a field for a list of the binaries themselves. This count in bytes is just, it's a denormalized data structure. This just makes it way more efficient to, we don't have to count the binaries every time we want to know what the count is. We just keep these counters up here at the top level and maintain them as we're putting stuff into the buffer and removing stuff from buffer. And so it starts off, as you might imagine, with 0 on the counts and no binaries. Start link in via tuple, pretty typical for a Gen server. Just giving it a name there. And then we, of course, allow for a lot of keyword ops to configure the behavior of this producer. So the caller or whoever starts this slot producer can pass in connection options, what query to use to start the replication protocol, etc. And then we pass those things all into state. And then we call process send after with a 0 to initiate the connect after we've booted. So we want to keep this init callback very quick because it blocks the whoever calls start link to start this process. We want to do this async. So after this Gen server has booted, we will receive a connect handle info, which we'll see just here in just a moment. And this is part of the GenStage protocol. We return a tuple that indicates that we are a producer, and we will not be receiving messages, but instead sending messages. We're the beginning of this GenStage pipeline. We'll talk about demand in a moment here. What I really want to focus on is the connect callback. So that timer we set when we first booted, send after connect, will get us here. And the first thing that we do is call Postgres protocol connect, passing in those connect options. And then we're connected. So if we get to this line here, it means that Postgres likes our username, password database. We have authority to connect, all that good stuff. So this, you're probably used to, if you've worked with Postgres, you're used to calling start link. That will start a pool of connections. Underneath the hood, those connections are calling Postgres protocol connect to individually connect to Postgres. So this idea of this protocol struct and working with protocol directly is probably something you haven't done before. But that's what we're just kind of going one layer deeper here as we need to, given that we're going to be doing a replication connection. So, but this connection, before we initiate the replication protocol, is the same. There's nothing special about this initial handshake or this connection. And then once we've connected to Postgres, we can then send our start replication query, which then initiates the replication protocol. So let me just show you what that query looks like. Just something like this. So start replication slot, sort of a funky syntax here. And so we have a replication slot. And then when we start a replication slot or start a connection to replication slot, we pass in the publication we want to use. And the publication indicates which tables Postgres should send to us. So you can say, send me all the tables. You can say, send me all the tables in this schema, etc. So that's all that does. Now, when we've gotten to this point, we've connected to Postgres, we've started the replication protocol, and we're going to put that stuff on state. And now we wait because Postgres is going to be sending us messages. That's what's going to happen next. So we can just put this stuff on state. We're done here, done connecting, no need to do anything else. If we can't connect for whatever reason, this is where we begin that reconnect loop, right? Very simple. But if we were started with a handle connect fail callback, this is where we can call that. So we can inject behavior like health, monitoring, alerting, whatever. And then we just send ourselves a connect after that reconnect interval. So that's connecting. And let's go down to receiving messages. So I mentioned that the next step is we'll be receiving messages from Postgres. If you've worked with TCP protocols before with Elixir, this will look very familiar. So we will receive messages as handle infos, and we have this guard clause when is socket message. So we just use this to discriminate between TCP messages that are coming over the socket from Postgres and other kinds of handle infos like the timers that we're going to be firing in this GenStage Producer. So if we go to isSocketMessage, we can see here it's a relatively simple guard that we've defined, and it's just looking for things that look like this. We're going to be receiving messages that have they're tagged, TCP with the socket that it's coming in on, the port it's coming in on, and then the binary here is going to be the third element, which is the actual messages coming from Postgres. If we initiated an SSL connection, then those will come in just tagged with SSL. And of course, if Postgres closes the socket, we'll get a TCP close. Other errors, we'll get other tags, but that's the idea. So that's the guard clause there. And so I'm going to show you in just a moment what these messages look like in their full, give you some examples. But we receive these messages in, and the first thing that we do is we call Postgres protocol handle copy receive. The reason for this name is that these are considered by the Postgres protocol to be copy messages. And we pass in just the whole message to the Postgres protocol, and it's going to return to us our updated protocol struct. So you'll notice we're going to just keep passing this handle in every time we call the Postgres protocol, and it's going to pass it back to us, as well as a list of copies. These copies, these are really the individual messages that Postgres is sending to us. These will be inserts, updates, deletes, etc. Then we're going to call handle copies, which we'll look at, to fold those copies into state, and then we might produce. So before we get into the rest of this stuff, let's see what these messages look like, right? So we'll do a DBG here on message, and then perhaps a DBG on copies here as well. And then we have a test that I can just fire up. And by firing up the test, we will be able to see these messages flow through. And whoops, just got to make sure I've been checking out a different branch, so some of the versions are messed up here. Okay, let's try that again. So here are just some example messages coming in from Postgres. This is the raw message, the TCP message, tag TCP with the socket it's coming in on, and the raw binary from Postgres. Don't be concerned, we'll talk more about these raw binaries a little bit later. You'll see this one corresponded to just one message. We passed it to handle copy receive, and it extracted just one message or one copy message from the full binary payload coming from Postgres. Sometimes that full binary payload, here's an example of one, will have two messages in it, which is the case here. And we can start to sort of parse out messages based on their message tags. So this message here begins with a 107, and that's a lowercase k, right? And that means this is a keepalive message. So that's how we're going to be able to discriminate these different messages, is by their message tags. And we'll talk more about keepalives later, but that's just the basic shape of the messages coming in from Postgres, or what I'm talking about when I'm talking about message and copies. And so handle copies, we just want to reduce over all the copies that we got and call some function to fold that copy into state. That's what we do here with the reduce while. And we're going to see all the fun that we can have with binary pattern matching in Elixir. It's really where pattern matching, it's one of the best places where pattern matching shines. This lowercase w means that this is a copy message. And then there's going to be a header. And then after the header, there's going to be another message tag here. It's going to be either an insert or an update or a delete. And then the payload for that insert, update, or delete, right? And so later on, we'll kind of get a little bit more into message tags. But for right now, we're just going to take this message binary. We're going to calculate like just make a guess on the internal size of this message in our system. And then we're going to update our accumulated message binaries data structure by just adding it to that, accumulating that message into those binaries. And this is how we just receive messages and accumulate them. After we've called handle data, we can talk, now we can start talking about production a little bit. So we're starting to accumulate these messages. They're coming in from Postgres over the TCP connection. We can call maybe produce every time. So we want to call maybe produce underneath two circumstances. So take a step back. With GenStage, this idea of producing means to send messages to downstream consumers. And we only want to send messages to downstream consumers if there's demand for messages. So if the consumers are ready to process more messages. So we might need to produce if we receive demand, because that might mean that we have accumulated message binaries that we need to send downstream, or we just got binaries in. We should check to make sure that check to see if there's any consumers that are waiting for messages downstream. So this is that latter situation where we just received some binaries, and now I want to check to see if anyone downstream is ready for them. So maybe produce, we have this guard clause that we only hit this when there is some demand downstream. And if there isn't, then of course we should just accumulate those binaries and not send them. Later, we can talk about how we can introduce some back pressure on Postgres so that we're not accumulating messages indefinitely if the rest of the pipeline isn't ready for them, but that's beyond the scope of this sort of first layer, this first commit. So in maybe produce, we can take our accumulated message binaries. We need to reverse them because remember we've been appending to the front. We'll split them based on demand. And then we just do some quick math just to figure out, okay, how much demand do we just fulfill? And then what is our new state of accumulated message binaries? This is all the bookkeeping around the counts and the bytes. And then we can return the binaries that we want to send downstream. These are really the produced binaries, probably be a better name. And then our next state, right? That's maybe produce. And so we call that right here, and then we return no reply message state. So we receive messages in from Postgres. We split them up into their individual copy messages. We're going to do more handling about those messages later. We accumulate them into state, and then we check our demand. And if there's any demand for messages that's overhanging, we produce those messages right away, remove them from state. And if, of course, there's any errors, then we are going to handle a disconnect. And handle disconnect is just going to, I don't know if I do anything right now, nothing right now, but eventually it will, in fact, this might be a problem. But yeah, eventually it will sort of reset our state, basically. This is not working right now. So with that in mind, handle demand probably won't be too surprising then, which is that when demand is sent from consumers to the producer, this callback is invoked, and we call maybe produce. And we just call maybe produce with the new demand. And we just see that if there's any accumulated messages, we can now fulfill the demand that just came in from downstream. So with all this context, you will now hopefully be able to understand the tests. There's maybe just one more thing, which is we've got this handle data clause for the copy messages. We've got one more for the keepalives. So remember that question mark K, those 107 messages coming in. This gives us a little bit of that. This just describes the protocol. And so Postgres will use, the keepalive is, we will have to eventually respond to Postgres to keep our connection alive. So most of the time it'll send you a 0 here at the end, which means you don't need to respond to me right now. And then once in a while it'll send you a 1 saying, hey, you should respond to me soon, otherwise I'm going to terminate this connection. And so we'll implement keepalives later, and there's a couple other nuances around keepalives that we'll talk about. In SlotProducer test, this is a true integration test suite. It's pretty nifty. We do use Ecto for this test suite. We have this table called characters. It's like characters in a novel or a movie or in a play that we will be inserting into a characters table. And because we're using Ecto, normally in test, Ecto uses a sandbox to isolate tests from each other so you can run tests concurrently in the same database. That test isolation uses, or the sandboxes, uses transactions. And we can't use transactions when testing the Postgres replication slot because Postgres won't send any messages over a replication connection until a commit has succeeded. So we need to do these tests async false or not concurrently. And we use what's called an unboxed repo. This is a term and sort of strategy borrowed from the Obin project. And an unboxed repo just doesn't use a sandbox. So we're going to actually be modifying the test tables. So we have to sort of manually deal with cleanup and whatever else. We also reset the slot between test runs by fast forwarding the slot to the end of the database. Between test runs is part of our sort of test isolation strategy. So this is perfectly, this is great because we get a bunch of integration tests and we can really truly test things end to end from Postgres all the way through our SlotProducer. Because we can't run these tests concurrently, you just need to be a little bit careful about doing too many of them. And you can imagine that stubbing out Postgres in order to have async tests is also desirable as a complement to these synchronous tests or these non-concurrent tests. In this test suite, we define a test consumer. And so we have the SlotProducer, and we want to attach a consumer to it to consume the protocol messages that it's producing. And that's what this guy does here. And so we're going to initialize it with a producer and a test PID, which is the PID of the running test ourselves. It's going to initialize as a GenStage consumer, and it's going to subscribe to that producer. And so in GenStage, when you have a consumer, you need to define a handle events function. And that handle events function will be called with events whenever they're ready for you, whenever the producer produces them. And so what's neat is that all you have to do as a consumer is just implement handle events. And then GenStage will take care of all the demand handling for you. So if your max demand is 1,000, min demand is 500, test consumer boots up, sends 1,000 demand upstream. And then after it has successfully processed 500 messages and sort of crosses that min demand threshold, GenStage will automatically send that new demand upstream to top it off. And so by just processing the messages and returning successfully, you are signaling that you have consumed those messages. So all you have to do is just create this handle events callback. And our callback is really simple. We just want to send to that test PID whatever message we received. So this is just a really simple way for us to hook into the GenStage pipeline and just see what messages are coming off of SlotProducer. So here's just some setup around some of our domain data structures. We won't worry about those too much. And this is the test that we have for this first layer of SlotProducer. So we can, we have our connection options. We'll talk more about restart wall cursors later. We just start the producer and the test consumer. We insert a character. And then we have some test helpers around messages and message kinds. So assert receive message kinds. We just have like a loop to receive all the messages and then a way to assert what kinds of messages we get. And we're just going to pluck off the message tag or the header from those messages that we got. And that way we can write a tight little assertion here that says exactly what messages we should have received. So we did an insert, and see if you can guess what each of these tags represent here. So this is a begin. So even if you don't commit an insert, update, or delete inside of a transaction, you didn't explicitly do a begin and a commit. In the replication protocol, all insert, updates, and deletes are wrapped in a begin and a commit. And that's how Postgres gives you metadata about the commit that the insert, update, or delete happened in. So we receive a begin, a relation message, an insert, which is this thing right here, and then the commit. So the relation message this describes the columns and their value types for the insert message we're about to receive. Postgres will only send this once per table in a given connection, just so that way you can now read all the subsequent messages for that table, because you might imagine that insert message we're going to get is very compact. It's not going to redescribe every time what all the column names are and all the column value types are, etc. So we get back brick here. And that is the first test. And that is the first layer of SlotProducer. So with really not that many lines of code here, and just under 180 lines of code, we have a working GenStage Producer that can connect to Postgres and begin to produce protocol messages. There's still several critical pieces missing here, and we'll get into those, but it's a really good start, and GenStage gets up and running quickly. So in this next layer of SlotProducer, in this next commit, we're going to annotate the inserts, updates, and deletes that SlotProducer produces with more information about the commit or the transaction that insert, update, or delete happened in. So inserts, updates, and deletes in Postgres, in the replication protocol, don't contain information about the commits. Instead, they are wrapped by a begin message at the beginning, and then the inserts, updates, and deletes that happened, and then the commit. So if you recall, we had that test that asserted BRIC was what we were going to receive for just a single insert. And we don't necessarily want to send those begins and commits downstream. We're going to want to process all these protocol messages in parallel. And so a much more powerful way to do this is to instead capture those begins and commits up here in the SlotProducer, annotate inserts, updates, and deletes with their commit and where they happened in the commit, and then we can parallelize everything downstream and then reorder everything later on with those annotations on the messages. So you'll see what I mean. So we'll go through the diff here in this layer. The first is to add a message struct. So before, we were just passing raw binaries downstream. Now with this message struct, we have some properties such as the commit timestamp, the commit LSN or the log sequence number of the commit. So this is the literal byte position in the write-ahead log of the commit. This idea of a commit IDX. So Postgres will only tell us the commit LSN of an entire transaction. It won't tell us the LSN of individual messages inside the transaction. But those inserts, updates, and deletes, they are strictly ordered in the write-ahead log. So if you insert a record and then update it and then update it again for whatever reason in the same transaction, those will be ordered strictly. And so their IDXs, indexes would be 0, 1, 2 in this example. And so we annotate messages with their position inside of the commit LSN. And we call this combination a wall cursor. So you'll see the term wall cursor a lot in the Sequin code base. And that's a combination of the commit LSN and commit IDX. It could be just a tuple. We end up representing it as a map of both, just to make it as hard as possible to screw up. So it's a map of these two concepts. But with these two, you then have a canonical address of a message that is not going to change. So if you were to restart the connection at any point in the future, you can guarantee that message will come in at the same commit as LSN and IDX. So you can also use this as like an item potency key downstream and all that good stuff. It's an identifier for that. It's an identifier for that specific change. We have this neat feature called transaction annotations, which we'll talk about. And then we just store byte size on this message as well. So this is an envelope that wraps the raw binary and gives and annotates it with information about the transaction that it occurred in, right? And where it happened in that transaction. So we make some changes to state, and the main things are adding some fields that allow us to track where we are inside of a transaction. So we're going to receive a begin message from Postgres. Then we're going to set these properties to indicate we're inside of a begin message. And then we're going to do accumulate some messages. And then we're going to receive a commit, and then we're going to clear these, right? So this is kind of part of our state machine for this connection. Accumulated messages then is updated as well because we're no longer accumulating binaries, we're now accumulating messages. So just updating that type definition as well. So that's the gist of the changes here, and we'll see how those come into play. And now we get to see something very exciting. If you don't have any experience with binary processing in Elixir, this is where pattern matching totally shines, as does the multiple function heads. So we're going to reduce over our copies, and we're going to call handle data for each copy. And handle data is now going to have multiple function clauses. These are going to keep expanding. And this first function clause that we've added, this again says that this is a copy message, which is what Postgres calls all the messages in the replication protocol. And then we pattern match on this next byte and say it must be a begin to hit this clause, or it's a begin. And then we get the rest of our message. So we can do this with begins, and then down here, do this with commits. And then we have we'll do this with relations. This should be, I don't know why I didn't follow convention there. Relations, and then, which we're not handling right now. And then the rest of the messages get accumulated here. So this is how we can begin to piece apart the business logic for all the different messages we receive. Inside of the begin handler, we decode the begin message, and we can make some assertions about the state of the world. So these assertions are just basically to prevent regressions. You know, we should never be in a situation where, for example, we receive a begin LSN that's bigger than the last commit LSN that we just processed. So these are just a way to help us quickly catch any bugs while still developing things or changing features or whatever. And then, of course, we update the state with the state of this commit that we just entered. The commit handling clause, again, is just asserting the state of the world. We're basically making sure that we're closing the open commit that is in state. And then we can close the commit, and that just nullifies everything. And then the message accumulation looks very much the same as before. There's one thing that we're missing here. I think we fix it in the next commit, but every time we receive one of these regular messages that we accumulate, we want to increment commit IDX, right? So we're going to do something like this. It had it. And so that way we can give every message we receive inside of a commit its own unique index. I think it just comes in the very next commit there. So with adding just those couple of clauses, those couple pieces of state, oh yeah, of course. we do those things to now track where we are in state, and then we need to create messages based on state. So here is our message struct now. This is the envelope. And we just dump the attributes of where we are in the connection, in the commit, onto the envelope. And there's the payload. So this is just changing accumulated messages to, or sorry, accumulated binaries to accumulated messages, but everything else is the same. So now our producer test, I think the next commit here will change our test. Let's go ahead and just jump up to that. So, yep, let me just add this here. Checkpoint 2. And let's go ahead and check out the next branch. Okay. So, and then I'll do the same thing I did before. And it's just let us see the diff. Okay. So I don't think there's any changes in SlotProducer in this next commit. Is that right? Oh, there is. There's a couple little changes. So yeah, we basically fixed the commit IDX there. And added a kind to the message struct to make it easier, basically in test, just to test the different kinds. And then right here in message from binary, we can just look at the message tag of the messages to add the kind to the message envelope. And that allows us to write some pretty cool tests. So this test was shortened because we moved some more of the setup into the setup block. And now, if you recall, before we were receiving, if I go back here, we were receiving BRIC. And now in this version of the test, we're just receiving insert. That's because we're swallowing relation messages. And in the begin, the commits are being folded into state as opposed to sent downstream. And now the consumer is just receiving the insert, which makes a lot more sense. The consumer can't really do much with the begin message. And so we assert that we receive that insert. And then, and this is using atom keyword or an atom as opposed to like the I, just because it's a little less inscrutable for future developers. We then also test that we produce the messages in the right order. So insert a character, update all, insert, update all, delete. And so we'd expect to receive this sequence here downstream. So this is really testing order of operations, all that good stuff. And this is a $10 test here, which tests transaction boundaries. So we insert a character, open a transaction, insert 2 more, and then we update that first character. We should receive 4 messages. And we do, and we also can assert here, and it's a little subtle with pattern matching here, but we assert that we receive the first message with 1 LSN, and then that the next 2 messages have the same LSN. So this is how we can assert they're in the same transaction. It's not super obvious, but we're using obviously Elixir pattern matching here. And these are both, in order to bind these to the same variable, they have to be equal. And of course, the commit IDX also increases, so we're testing this as well. And then we receive a 3rd LSN, and this should reset. And so, some basics there. We could also assert that the LSN's like incrementing and stuff, but that doesn't seem super necessary, and that's really Postgres' job. So that is the next layer. Let's keep going up. So that was checkpoint 3. And now if we go up to checkpoint 4, I'll do the same trick here. So in this commit, in this layer, we begin to implement acks. So let's talk a little bit about how acks work, or keep alive messages. So Postgres sends us messages. There's only really one kind of message that we will send back to Postgres as part of the replication protocol. and I forget the formal name. It's like a keep alive message. And in that message, the message serves two purposes. The first purpose is to keep the connection alive. So if we don't send that message on a regular interval, then Postgres will terminate the connection. It's just not sure if we're alive or we're well. The second purpose is that we tell Postgres what messages we have safely committed, and therefore it can safely purge. So if Postgres sends us an insert, update, and delete, it's not going to purge those messages from the replication slot right away because it sent them over TCP. It doesn't know yet if we receive them. And furthermore, it doesn't know if we've fully processed them. So let's say that we were implementing a replica Postgres database. Well, we might receive messages over TCP from the primary Postgres database and then buffer them into memory and then flush them to disk in a batch, for example, right? And so we don't just want to tell Postgres the moment we receive, or the primary, the moment we receive the messages, hey, it's good, I got them. We, of course, want to wait to acknowledge those messages until they're flushed and in a location that we think is secure in case we were to crash immediately afterwards. So that's another way to think about this is like an acknowledgement. And we're going to call this, I think in this commit, we call it the safe wall cursor. Again, the wall cursor being the commit LSN and the IDX inside of the commit that we consider to be the marker there. But eventually we just consolidate around the name restart wall cursor. So you'll probably see both of those interchanged here, safe wall cursor and restart wall cursor. Postgres sends us an insert, update, delete. In Sequin system, these are going to be in flight for a little bit after we receive them. They're going to be in memory, so we're trying to deliver them to downstream sinks. And then once we've written them to Kafka or SQS or whatever, then we can consider those to be good to go. So if these all belong to the same, let's just say these all belong to commit LSN equals 555. So if these all belong to that commit LSN, once they're all flushed to downstream sinks, then we got a green check mark here or whatever, and we can basically say, cool, the safe wall cursor or the safe restart cursor is now commit LSN 555. We can acknowledge this and we'll send it back to Postgres. Now it's very important that we do this on a regular interval for two reasons. One, if we don't do this, then Postgres is just going to hang on to all the messages it's ever sent us. And that's going to cause the replication slot to balloon. And eventually you're going to run out of storage. Terrible. The second reason you want to send these regularly is that if we disconnect from Postgres and we reconnect, Postgres is, of course, going to replay from the very beginning because it doesn't think that we safely process these messages. So it'll go all the way back and give us the insert, update, delete again. Very inefficient. Every time we reconnect, we're replaying all these messages that we've already processed. So that's the concept of acks and safe wall cursors or restart wall cursors. So when we boot, we schedule a timer, send ack, and we can just have that timer run every second, every 10 seconds. There's really no reason not to run it quite frequently. And you'll notice that if we're disconnected, we can't really do anything. So we just schedule the ack to run again. If we are connected, then we can prepare an ack message. And that ack message, why is this not jumping here? Okay, this commit might have us in a partial commit state. I think this will show up in the next commit. This ack message just contains the LSN that we want Postgres to advance the wall to. And so we're going to store the safe wall cursor on state. We'll talk about that in a moment. And Postgres doesn't have the concept of a commit IDX. So we're just going to tell it the last commit that we have safely flushed downstream. And then we're going to schedule that next ack and then use protocol handle copy send to send the server that acknowledge message. So just on that timer, just sending this ack message. So the important part, this timer is pretty easy or pretty simple in terms of just run a timer, send an acknowledge to Postgres. The much trickier part is how you determine what the safe wall cursor is or what the safe restart cursor is. And so I think in this commit, yeah, we just have, I think, some hand wavy stuff going on. So we have a similar timer for update safe wall cursor. So every, 10, 20 seconds or whatever, you loop through and you call update safe wall cursor. And again, I think this commit is missing some stuff. We can see if the next commit has them all. But to get started, yeah, SlotProducer is just going to accept a function from whoever starts it. And that function will return back the safe wall cursor. And that's because, especially in Sequin system, to calculate the safe cursor to send to Postgres is pretty complicated and involves a lot of downstream checks to see what messages have successfully been flushed to sinks. So SlotProducer shouldn't know anything about that. Instead, it'll just call this function to get that safe cursor. It'll put it in state. And then the next time we call send ack, it'll pull that off state and send it to the server. So I don't think we have any other tests associated with this here. There was a brief moment where we were sending relation messages through downstream. Okay, right. No, this test is really valuable. Let's talk about this test. So this is a great test because it tests a lot in a very compact area, and it's a full integration test around acknowledgements. And this gives you a good idea of how this will work. So first we have this tag which says don't start SlotProducer. So we're going to skip the setup block that starts SlotProducer. The first thing we do is we query Postgres directly to get the confirmed flush LSN or the restart LSN of the slot. Interchangeable terms for the purposes of this conversation. So this is just the current position of the replication slot. This is our initial LSN. We're going to use an agent as a way to control what the safe wall cursor function returns. You'll see this come into play here, but we start this agent and it's just going to return some LSN, some IDX. We start the SlotProducer. Remember how I mentioned I like to have these intervals be configurable. This is why. So we pass in very short intervals, 1 millisecond each, for acking and updating the cursor. So that way this test won't take a very long time to run. We're going to constantly be calling these functions. And then we pass in as our safe wall cursor function just a get against this agent. We're going to, so we started the SlotProducer. We're now going to insert a character. We should have received that message. And then we're going to call agent update to ensure our agent now returns this next commit LSN, which is pretty much what our system would do. Is it would after this character flush to Kafka or whatever, this would become the new restart LSN in our system. So note we start the agent. We're calling the safe wall cursor function every millisecond, and it's returning the same initial LSN. After we do this insert, we update it, so now it returns this new LSN. So now the safe wall cursor functions return this new LSN. And then we are calling the send ack function to send the safe LSN up to Postgres. And so this is the really valuable line right here. This is the full assertion. We are using this assert library called assert eventually. It's great for Elixir. Very simple. You can just give it an assertion and it will just keep running that assertion until it passes. And it has like a 1 second, as 1 second to start to pass basically. And it's going to call Postgres to read the current LSN of the replication slot until it matches the next commit LSN. So just think about what this test is covering. It's covering quite a lot. It's asserting before we start Postgres or before we start the replication connection, the LSN is at one position. And then we start the connection, we insert a character, we change the safe wall cursor function to increment to that new commit LSN, and that new LSN flows through the slot producer all the way up to Postgres and then is reflected in the state of the replication slot. So it's a really fantastic test. We didn't really have to actually insert anything here. We could have just returned any commit LSN, but this just kind of really simulates a real world situation here. So that is this layer, and that is sending acks to Postgres. Again, there's a very deep art in determining what the safe restart wall cursor is to return to Postgres when you have a highly concurrent downstream system delivering to sinks, but that's out of scope for now. Let's go to the next layer here. I think we're getting close. So we'll add these back in. And then we will check out 5. And it's possible that 5 just fixed some of the issues. Yeah, okay. So 5 is just bringing us a little closer to something that's production ready here. So I think, yeah, the last commit was missing some of the stuff around these timers, tracking them in state. After we boot up, we call schedule timers, which schedules the timers for both acks and updating the safe wall cursor. And we'll talk about transaction annotations next. Those are really neat. If we're disconnected, we just properly sort of handle the reset that we should do to state. So we should just close any commits that were happening if we're disconnected. Here's that ACK message I was talking about that we're sending to Postgres. So there's different types of LSNs. We just send the same LSN for confirmed and flushed and restart. We ended up moving the start replication slot command into this file. There's really only 2 that will ever run, so it doesn't make a ton of sense for the caller to need to be able to specify the exact command. Instead, we can just switch off of the Postgres major version. There's a slight difference that we make depending on the version on this initial command here. Great. Okay, so that's it for this layer here. And let's talk next about transaction annotations. Do we have a test for that in here? We do. Okay. So Sequin has this really neat feature called transaction annotations. Transaction annotations allow you to use a built-in Postgres function called PG logical emit message. And in the prefix, you can indicate you want to set or clear transactions or transaction annotations. So what I mean by that is if you call PG logical emit message Sequin transaction annotation set, you can pass in a JSON object with things like with metadata around the transaction, like the username of the user that made the change, the source, they use the web UI, their request ID. So this lets you add metadata to messages inside of a transaction that you wouldn't normally be able to infer based on the insert, update, or delete messages themselves. So we add a new handle data clause. This one matches on logical messages, M. And logical messages have a prefix and content. And so we can also just match on the fact that the logical message has this prefix here, Sequin transaction annotations. And if it does, then we enter this function clause. So binary pattern matching, super sweet. And the prefix is separated from the content with a null byte. So we're able to get the operation here and then the rest of the content, the rest of the binaries of the content. And then if the operation is a set, then we add to our state the transaction annotations, that content. If we're clearing, we nullify it. And that's pretty much it. And then by setting the transaction annotations here on state, then when we create the message, we just dump those transaction annotations on the message. And then when the commit is finalized, the state transaction annotations is nullified, or if the user calls clear, it's nullified. And then all subsequent messages don't have those annotations. So it is sneaky easy to do. And this just kind of swallows other kinds of logical messages. So the tests for this are pretty sweet. We insert a character. This is the last one. Here we go. So inside of a transaction, insert a character. We write this annotation message. So this just calls the, select PG logical emit message function. And we enter 2 more characters. And then we should receive out the other end that relation message, a message without transaction annotations, and then 2 messages with transaction annotations, the same annotation coming through on both. And then we just make sure that when we clear them, they're cleared. So here we write one, insert a character, clear it, write a character. So the first one has an annotation, the second one doesn't. We have relation messages in here. We end up removing this and fixing the commit IDXs, because this is actually not great behavior. We don't want the relation messages to come through, and we don't want relation messages to affect the commit IDX, but that comes later on. So that's transaction annotations. That might be everything for this current stack here. Let me just find out. Okay, that's an overview of the initial foundation of SlotProducer. At this point, we have a producer that produces Postgres protocol messages for downstream consumers. It annotates them with information about the transaction that they were in. It handles the connection to Postgres. It sends those keepalive, those acknowledgement messages to Postgres. This is really a strong foundation that we continue to build on to our production SlotProducer that we have today. We can check out, there's a lot more to the rest of the data pipeline that I'd be happy to get into in a future video. But let's just take a look at where this is today. So in terms of lines of code, we saw it go up to about 800 lines. Yeah, it's really, there's really not too much more happening inside here now. There's a little more sophistication, obviously, the sort of tweaks that you make as you get something into production. But the main thing I wanted to do was a little demo to show how this all works end to end right now. So I've made a test processor. So normally we connect the SlotProducer to our full Sequin data pipeline. And that data pipeline parses the messages, reorders them, and delivers them to downstream syncs. There's multiple stages to that pipeline. Just to kind of isolate the SlotProducer and see it in action, I've created a very simple GenStage consumer called test processor. And this is very much like the test processor that we were using in the SlotProducer test. It's going to boot up and subscribe to a producer that we start. And then it's just going to DBG the different messages that it gets. So you can see this working end to end. And we're going to actually use a Postgres database to see all this. So I've also gotten a little have a little startup script here that we'll use. So the SlotProducer on main right now expects a number of keys in order to boot. So it needs some IDs, which it uses for logger metadata. It needs to know like the slot and publication to connect to, the PG major version. And then there's some other things here related to connecting to the database. And I mentioned that the restart wall cursor function is something that you just inject into the SlotProducer, and then we have the complicated logic around how to compute this elsewhere. But for now, we're just going to have it not actually increment the cursor at all, just to keep it simple. And then we're going to start the SlotProducer and then start the test processor. So we can go ahead and run this. Let's just start this bit here, and we'll get a console going. So I just need to reinstall this. Call make dev, and then Sequin has a lot of log output in development. So I'm going to switch over to another tab. And this is just going to connect an IX shell to that other node, but then I don't have to worry about all the log output. And we're going to start SlotProducer. So SlotProducer logs that it's now connected, and we're going to see it send its ACK messages to Postgres. We have an active project we're working on to basically send ACKs every second because we don't see a reason why not. But there's a couple of things we have to do in order to make that possible. So right now, because the restart wall cursor function is basically an identity function, it's just returning the same cursor, we are not going to advance the replication slot at all. So we're just going to send the same ACK message over and over again with no bytes advanced, but that's totally fine for our test. And this will at least keep the Postgres connection alive. And now we can start the test processor linked to that. So the test processor is now running. And you'll notice that when we started the test processor, we got some messages. And that's because there were some messages in the replication slot that were buffered by the SlotProducer, and now it's sending them to this new downstream consumer. But let's go ahead and just create some messages from scratch. So I've got a connection to a database here, and we can take a look at it. It's just a Claude generated table with some example data. So we can just update this first record here and see it flow through. So if we do update demo products set ID equals ID, where ID equals 1, we just want to trigger any sort of event here. And if I go back to our shell, let me clean this up here. You'll see that this event flowed from the SlotProducer down through the test processor's handle events callback, and we can see the payload right here. And this 85 is going to be an update. So this is the update message all tagged up here. And we also get the commit LSN. Of course, it's the 0th thing in there. If we update a bunch of them, update 8, we're going to receive a bunch of messages, and then we'll see those commit IDXs are increasing all the way up to 7, which makes sense because they're all inside of the same transaction. One last thing that might be kind of interesting, just to close this out, is I can show you what these messages look like when they're parsed. So we can do an enum each on the events, and then we have a decoder in here that we can use, decode message event.payload. So let's go ahead and dbg that. Okay, and now we should be able to just hot code reload that, clear that out, and do an update on just one of them. And you can see this converts the binary payload into an Elixir struct, and you can see an idea of what information is carried on that binary. And the main bit here is the tuple data. And so Postgres doesn't send you, of course, the column names and values every time. It just sends you the values. And this is the latest record values here. We have to do our own work to parse these into the right format, right? Look at this date time here. You'll also receive the old tuple data if you turn on replica identity full, which we have you do when you use Sequin, but that's the idea. So there you have it. We have SlotProducer. It's doing as minimal work as possible and delegating downstream in the full Sequin data pipeline. The next stage is a fan out to a processor stage where we take these raw messages like this, like the binary, we decode them into Elixir structs, and we parse the values and make them into the much richer data types that are desirable. And then we match them to downstream consumers. So, oh, this message is intended to go to this downstream Kafka topic. Then the stage after that is we make sure that we basically join all these concurrent processors to do the reordering to make sure that we can deliver things in order downstream. So I'll get into all that stuff in a later series here, but hope you enjoyed this look into GenStage, Sequin, and the Postgres replication protocol. Thanks for joining me.